Well,
Hello, and welcome to another exciting adventure in the New York City Category Theory Seminar. This week we have Prakash. Prakash is speaking on quantitative equational reasoning. He's from McGill University. Prakash, take it away.
thank you. Thank you for inviting me to this seminar. I was told to give 4 pieces of information about myself, and I'm not sure if I remember what they all are, but you prompt me. My name, Prakash Panangaden.
No. Your name we have, although you can pronounce your last name again. Where you were
Panangaden.
born?
Okay, so where I was born in a city called Pune in the west.
Outside of Mumbai.
It's about 150 kilometers east of Bombay, as I'll still like to call it. And I was even told to say the open set in which I was born. So the neighborhood in which I was born is called Khadakvasla, and it was an army base because my father was in the army and I was born in the military hospital where my birth is recorded as boy. Anyway, so what was the next thing? Baptism?
Oh,
No.
where you got your bachelor's and where you got your PhD?
Right. So it's a bit difficult to say where I got my bachelor's since I never got one, but I got a 5-year integrated MSc from Indian Institute of Technology, Kanpur, which is a place in India. And then I got my PhD in in physics at the University of Wisconsin, Milwaukee, and I am now in the computer science department of McGill University, and also a member of the Montreal Institute of Learning Algorithms, affectionately known as MILA.
Very
Okay.
nice. Well,
Thank you.
what is that Institute of Learning Algorithm? Where is that? What is that affiliated with?
It's affiliated with McGill and with the University of Montreal.
Very nice. Okay, take it away.
Right. So what I'd like to talk about is work that I've been doing with Radu Mardare, who's at Strathclyde, and Gordon Plotkin, who's supposedly at Edinburgh, but is actually everywhere else, mostly in California. And this all started one day when Gordon and I were both lecturing at a winter school in Estonia, of all places. And I was lecturing about the stuff I usually talk about, which is probabilistic systems, probabilistic bisimulation, and so on. He was talking about equational reasoning about programs, and basically the connection between monads and equations and operations which define those monads. So, and then he said to me, we should put these things together. And I was trying to sleep on the bus, but he wouldn't let me. So I stayed up, and the germ of this theory developed there. So it led to what I'm going to talk about today, quantitative equational reasoning, which, as you might guess from the name, is a variation on standard equational reasoning. And what I'm going to do is review basic notions of equational reasoning, which I'm sure all of you are thoroughly familiar with, but bear with me because I want to then redo it in the quantitative setting. And now I'm hoping, so I'll begin with an introduction, and then I'll talk about the standard equational reasoning, which has been around for nearly 100 years since the work of Garrett Birkhoff and others. And then I'll talk about metrics, which are essentially the quantitative analogs of equivalence relations. And then I'll introduce these quantitative equations, and finally I'll give some examples. Now, often these examples are at the end, as you know, like this is just an example to illustrate the theory. But for me, it was the example, one of the examples that I'm going to show that made this interesting to me. Otherwise, it would have just been more theory for its own sake, but it wasn't. It was really a interesting and fascinating example. So equations are at the heart of mathematical reasoning. I believe somebody once told me, I don't know if this is actually true, that the pair of equal straight lines that represent equality is the oldest known mathematical symbol still in use, being nearly 2 millennia old. Reasoning about programs is also based on program equivalences. So this is something that transcends pure mathematics. It's also exactly how one reasons about programs. And there's a trinity of ideas connecting these notions. One is in algebra, one has kinds of algebras given by equations. So these are what one is used to. These are equational varieties. Lauvier showed how to get away from the details of one presentation and gave this abstract thing called a Lauvier theory, which captures what's meant by an equationally presented algebra. And then the connection was made to monads, where monads give rise to an Eilenberg-Moore category, which is exactly the category of algebras that one was talking about in the first place. So these are, I don't want to say three sides of a coin because coins have two sides, but these are essentially three vertices of a very intimately connected triangle. But to rip off a phrase of David Mumford's, this is the dawning of the age of quantitative reasoning. And so it became, we want a quantitative analog of the whole notion of algebraic reasoning. And the basic substitution that one is going to make is that instead of trying to capture equivalence relations, which is what one does with equational reasoning, we're going to try and capture pseudometrics. And syntactically, what we're going to do is just introduce the equality symbol, but now indexed by a real number. So it looks like a hack, in fact, but as we shall see, it has a beautiful theory all of its own. And just like ordinary equations are linked to monads on set, these will turn out to be linked. The algebras defined in this way will turn out to be linked to monads on met, where exactly what met is, I'll specify a bit later. So let me begin my review of undergraduate equational reasoning by going back to finitary equational theories. So typically one has a signature, which means one lists some operators, each given some arity, which is simply, for things on set, the number of arguments that the operator takes. Then one constructs terms out of variables and these operators, some of which may be constants, so zero-ary operators, and one builds up terms in the obvious inductive way, here given with this computer science notation, which is shorthand for inductive definition. And then one introduces equations between terms, and of course these equations may contain variables, so they might stand for rather generic statements. And so you then have axioms, which are simply sets of equations characterizing certain structures of interest. And finally, there are deduction rules for reasoning about equations. And these rules are the usual ones that one associates with an equivalence relation. They're also the rules for a congruence. And having set all this set up, then you have theories, which are simply the complete set of equations closed under all deductions. So what are these equational deduction rules? So if S equals T is one of your axioms, and of course you can deduce it from the axioms, then the usual rules for equations, namely transitivity, symmetry, and reflexivity. The congruence rule basically says if you have equalities and then you apply the same operator to tuples of terms which are correspondingly equal, the resulting terms are themselves equal. So all very standard notions of equational deduction. And finally, one may substitute terms for variables in the usual way. And if the terms T and S were equal, then substituting for the same variable X on both sides, the same thing, will also result in an equality between new terms. And U, of course, may contain yet new variables. So that's the basic setup for how you have equations and how you reason with equations. So you can describe algebras equationally. We assume, just for simplicity, that there's only one basic set of things, one sorted algebras. And then for each set of operations, for each operation, we have an arity. And this collection of operators with arity is called a signature. I'm going to assume everything has finite arity, though of course now categorists have known for a long time that you can introduce infinitary operations very smoothly. So an omega algebra, once you have the signature omega, is simply a set to interpret the basic sort, and for each operation f of arity n, a function that goes from a to the n to a. So given this setup for defining algebras, it's easy to define the notion of homomorphism, maps between algebras that commute with the basic operations. It's equally easy to define subalgebras, which are also closed under the operations. And then you have to say what it means to say that the algebra satisfies a certain equation. Now, given a set, we can define the term algebra generated by X. We'll write this as T of X. That simply means we take the elements of X as if they were new terms and then build up terms in the usual inductive way. So the elements of X themselves are in T of X. Then if T1 through Tn are in T of X and F has arity n, then the same inductive definition goes through, and F applied to those terms will be another element of T of X. And now we want to say things like this. For example, we might want to say this particular equation, which smacks of associativity, holds in a particular algebra. And now we think of this X as elements of X as variables. So we will say that an equation holds in an omega algebra if for every homomorphism from the term algebra T of X, constructed from the variables in the terms, to the algebra, we have H of S equals H of T, where now the equality sign here means identity in the algebra A. Supposing we have a set of equations between pairs of terms in X, we can define a congruence relation in the evident way. And it's easy to check that this is indeed a congruence, namely it's respected by the operations. So we can define the operators acting on the quotient space in a sensible way, and that will all be well defined. So from this way, we get a class of algebras satisfying a set of equations. It's called a variety of algebras, not to be confused with an algebraic variety, which is a completely different thing. So one might ask, in this kind of logical system, without any notion of negation, when do we say that a set of equations is bad or inconsistent? So if you can derive the equation x equals y, where x and y are just variables from S, then the only algebras around have one element. Because if x equals y and x and y are algebras, then any substitution can be done independently on the two sides and all things will be equal. So this is, we will say things are inconsistent if you can derive that equation. So all the algebras you know and love are examples. Monoids, groups, rings, lattices, Boolean algebras are all examples of what I've just talked about. Vector spaces, essentially, yes, but they have two sorts, but otherwise they're the same. Fields are an annoying exception because we have to say if x is not equal to 0, then a certain operation exists. And fields, in fact, do not form an equational variety. They can't be defined by equations. One might have thought perhaps this was just a clumsy way and there's a cleverer equational, purely equational presentation, but it actually follows that there is no such thing. Sometimes we need to state conditional equations. So one nice example in computer science are cancellative monoids, of which the canonical example are strings. So if x concatenated with y equals x concatenated with z, where x, y, and z are strings, then x equals z. So this holds despite the fact that this is not a group and you don't have inverses to do the cancellation for you. Another very computer sciencey fact, stacks are equationally definable, but queues are not. Now,
is there a way to see that, why stacks are and queues are not?
yes, there are proofs of these things, but not completely
Not
elementary.
civil. Okay.
Well, stacks, it's easy to see because you write down the equations.
Right.
Queues, the intuition is you add at one end and remove from the other end. And so it's not easy. And then, of course, the queue can be of unbounded length. So it's hard to write down one equation that's going to cover all possible different lengths of queues. That's an intuition, it's not a proof, but that's basically kind of why you can't do queues.
What type of structure does a queue have? In other words, is it a finite limits sketch or something?
Is it a finite limit sketch? I don't know. Mike, do you know? I don't know. I would think not, right? Because if it was, it would be, yeah, I don't know. Anyway, I'd like to show you another algebra, which I'm going to talk about a bit later on, well, quite a bit later on. But this was one introduced by Marshall Stone in 1949. And it has uncountably many binary operations. So it has the plus symbol indexed by any real number between 0 and 1 inclusive. And of course, rather than keep you in suspense, it's meant to abstractly capture the idea of convex sums. So the axioms for it are what you might expect for convex combinations. If I make a convex combination of t and t prime with the weight 1 on t, then there'll be no t prime in it. It'll all be just the same as having t. And if I take the convex combination of t with itself, then it doesn't matter in what ratios I mix them. It's still going to give me t. There is a commutativity rule, except that one has to do a bit of gymnastics with the subscript on the plus. So epsilon has to be changed to 1 minus epsilon. So we should think of t plus epsilon t prime as saying, take epsilon of t and 1 minus epsilon of t prime and put them together. And finally, there's an associativity axiom where, again, the S means skew. So it's a skew associativity axiom. There's some small chance that this gymnastics I did with the subscripts is actually correct, but you should believe that some formula like that should be the right one. So this is a nice algebra, lots of operations, but it is otherwise completely fitting into our picture of what constitutes a finitary algebra. So if you look at the collection of all algebras satisfying the equations, it becomes a category if we take the morphisms to be homomorphisms. And if you take X to be a set of generators and we construct T of X in the way I described, you take the terms, you define the evident congruence relation and quotient, then there is a map from X to T of X, which basically is inclusion of generators. You map each X to the equivalence class of that X under this equivalence relation. And this has the well-known universal property, namely, if I take an arbitrary map from X to the carrier set of some algebra, then that can be canonically extended to a homomorphism from the term algebra to the algebra A. Okay, so this is what makes the term algebra special. It's universal. There are some lovely theorems due to Birkhoff, and many extensions of these have been done by many people since then. Adamek, Mike Parr, and various other people. So Birkhoff's theorem says a collection of algebras is a variety of algebras, namely equationally definable, if and only if it is closed under homomorphic images, subalgebras, and products, possibly countable products, not just finitary products. And there are various analogous theorems for things defined by horn clauses, quasi-variety theorems, things defined by horns. I remember Mike Parr's lecture in which he did this and said things can be defined by horns. So, so you have variety theorems. So all this, so this allows me to tell you why fields are not an equational variety. Consider the simplest field, and you take the product with itself. And now, of course, everything is going to happen pointwise in Z2 cross Z2. And now note that 1, 0 times 0, 1 is 0, 0. So this thing, Z2 cross Z2, whatever it is, has 0 divisors. It is certainly not a field, so it's not closed under products. You have no hope of defining it equationally. Okay, now let me switch gears to metrics, which is the other piece that I have to add to the equational stuff to get quantitative equations. So these are the quantitative analogs of an equivalence relation. So a pseudometric is a map from M cross M to the non-negative reals, and it has the axioms you expect, the triangle inequality and symmetry. Instead of the usual axiom which says dxy is 0 if and only if x equals y, all I'm requiring is that the distance of a point to itself is 0. I am permitting two distinct points to be at 0 distance. That's how it differs from a usual metric. So pseudometric is a slightly more liberal thing. And if indeed we have that stronger assumption, then we have what's called a metric. And we can define the usual notions of convergence, completeness, topology, continuity, etc. with metrics or with pseudometrics. Of course, with pseudometrics, you won't get many of the properties you're used to with metric spaces. Metric spaces are always Hausdorff, but of course, pseudometric spaces need not be. The relevant maps are non-expansive maps. So this means that when you map from one space to the other, the distances cannot be expanded. They might shrink, they might even be the same, but they cannot expand. And this property it automatically enforces continuity in the usual topological sense. So we will define the category met to have as objects metric spaces, and I should have said explicitly on this slide, extended metric spaces which may take infinite values. So it's possible for the distance between 2 points to be infinity. It turns out that the category of extended metric spaces is much nicer. It has arbitrary coproducts, for example, whereas met does not. Again, I'll take the morphisms to be non-expansive functions. Extended metrics are not particularly scary. They nicely decompose into coproducts of ordinary metric spaces when you take the components to be all those things at finite distance. And what's going to happen is that quantitative equations are going to give us monads on met. Now, it's going to be interesting later on to define metrics between probability distributions. So let mu and nu be two probability distributions on a given space, X, equipped with the metric and with the sigma algebra of Borel sets generated by the topology of opens given by the metric. The total variation distance, or TV for short, tells you take any measurable set and look at the difference in the values that the two measures mu and nu assign to that set, and then soup over all possible sets. So that gives you one measure of how far apart mu and nu are. Okay, it's clearly a metric because if they are the same, then they'll agree on every set. And if they agree on every set, then you might as well call them the same. Okay, another very interesting metric is the Kantorovich metric. So here you say, I'm going to take all possible functions and integrate them with respect to each of the two measures, and then I'll compare these integrals. And then I'll soup over all the possible functions. It is important to control the functions, because if I just allow you any old integrable functions, you can kind of exaggerate that function exactly on the places where mu and nu differ, and you can make them arbitrarily exaggerate how different these integrals are, even though mu and nu might not be that different, and this soup will always be infinite. So you can't allow me to just use any old measurable functions I want. You have to control them in some sensible way, and the standard way introduced by Kantorovich is to require that the functions f be non-expansive. Now, there's a completely different metric which one could define, and I'm going to spend a few minutes defining it. So, given two measures, one important structure that you can introduce is what's called a coupling. The way to think about a coupling is, imagine that the two measures represent piles of sand. So you've got a measure mu, it's a pile of sand on your space X. Nu is a different measure shaped differently. And what you would like to do is to move some sand around in such a way that the mu shape gets transformed into the nu shape, right? So of course, there are many ways of doing this. And each way of doing this corresponds to telling you, move this much sand from this spot to that spot. In short, you can describe a plan for moving the sand around by a measure on the product space whose marginals match with mu and nu. Okay. So this space is called the space of couplings. So a coupling is simply a measure on the product space such that when you project it onto one axis, you get mu, and when you project it onto the other axis, you get nu. So you should intuitively think of this as a transport plan. How much does this plan cost? Well, what it costs depends on how far you move it. So you integrate the metric with respect to this coupling measure on the product space. And so this says, I've now got kind of the weighted cost of moving each thing around, the weighted distance, if you like, that I had to move things around. And now what you do is you minimize that cost by choosing just the right coupling. So the minimal cost coupling gives you another metric. This is this metric, which is defined completely differently from the Kantorovich metric above, is in fact equal to the Kantorovich metric. And the fact that these two metrics are equal is a well-known theorem from 1958 called Kantorovich-Rubinstein duality. It's called a duality because one's a soup and the other one's an inf. These are, of course, great theorems when you can have them, because it allows you to do things that either one alone could not do. This is often called in the literature the Wasserstein metric, but I don't like to call it that because Wasserstein had nothing to do with it. Kantorowicz's work was in the 40s, and this Kantorowicz-Rubinstein theorem is in the 50s, 58, in which they proved this duality. And Wasserstein's paper, which everyone cites, is in 1969, where Wasserstein never claimed to have invented this metric. He used it in passing, doing something else. But for some reason, this name has stuck. So I like to call it the Kantorowicz metric, whichever way it's used. Now, there's a variation on the original Kantorowicz metric, which was, instead of integrating the metric, you integrated raised to the pth power, and then you take the pth root of the resulting integral. So this is kind of an LP-like analog of the original W metric. I think one of the problems is that Kantorowicz used the letter W in his name for the metric, which is always a grave mistake. Always use your own initial, not somebody else's, when you're naming things. Okay, so now finally, let me get to quantitative equations. As before, we have a signature omega, variables x. We construct terms in the usual inductive way. And now I'm going to define quantitative equations, which are S equals sub epsilon t, where S and t are terms, and this epsilon is going to be a rational number. Now, this is a hangover from old days when we used to insist on these distances being between 0 and 1. But in fact, it makes more sense to allow them to be arbitrary, including possibly infinity. Anyway, 0, 1 is the same as 0, infinity in some sense. So I prefer to work with extended metrics these days. A substitution is simply a map that says for each variable x, I can write a term t of x, and I'm going to write capital sigma sub x for the set of such substitutions. And of course, any such substitution extends to a map from the whole term algebra to itself, which will be a homomorphism. I'm going to generalize quantitative equations to now have hypotheses in front. So we'll call them quantitative inferences, where I'm allowed to have some finite set of assumptions written as equations, and then I have some conclusions. So these judgments or inferences will be the building blocks from which I will do reasoning. So we're going to require the following properties to hold: reflexivity, so every term is at 0 distance from itself. So equal sub 0 corresponds to the old-fashioned equality that one was used to. We have symmetry. We have the triangle inequality, which is so the way you should think of this equation, maybe the next one makes it clearer, is that when I say t equals sub epsilon s, what I mean is the distance between t and s is at most epsilon. So it could be less. So of course, if t equals sub epsilon s is a true equation, then if I add something to epsilon, it's still a true equation. I've just made the bound a little looser. Now here is an important infinitary rule, which we call continuity. And it says if I have essentially a sequence of epsilon primes converging from above to epsilon, and for each of those epsilon primes, I can prove t equals sub epsilon prime s, then the limit value also follows. Okay.
Well, 1 second. So each E sub epsilon is not an equivalence relation.
No,
but all of them
not.
together gives an equivalence relation or something?
No. Okay, so I'm glad you asked that. So there's a direction that we could have followed and we didn't. So I don't know if you're familiar with the concept of uniformity. They lie between metrics and topologies. So uniformities are defined as families of subsets of x cross x rather than as subsets of x, and they're required to satisfy certain axioms. And just as topology gives you the framework to talk about continuity, and metrics gives you the framework to talk about isometries, Uniformities give you the framework to talk about uniform continuity in a non-quantitative way. Fact, this entire ensemble of equational, of binary relations, i.e. the equal sub epsilon, you take them as one ensemble, they precisely form a uniformity. So there's a nice book by James called Uniform Spaces, which tells you the basics of the theory of uniformities. And I actually love uniformities because, for example, completeness is not a topological property. You can't talk about a complete topological space. It's metric spaces that are complete because you can talk about there being Cauchy sequences that ought to have limits. But uniformities, even though they're not quantitative, allow you to talk about nets being Cauchy. And so you can talk about completeness in the uniformity world without going to the numerical world of metrics. So yes, they form something. They're not just randomly there. But definitely it is not true that each one of them is an equivalence relation. Absolutely not. So I don't have transitivity, I have triangle. So when I chain these things together, I start accumulating epsilons. So one has to think about the ergonomics of reasoning in this setting. Whereas in some sense, equational reasoning in the traditional sense was free. You chain them freely and doesn't cost you a thing.
So just one second. So what exactly is the generalization of an equivalence relation, this uniformity thing?
It's not a generalization of an equivalence relation. It is a new kind of structure that you can put on a space, and you put it on the space. It is a collection of binary relations that's required to satisfy some axioms. For example, every one of them must contain the diagonal, and so on and so forth. There are a bunch of axioms which I don't want to go into, but they have nice structure.
Okay, thank you. Go on.
Some other time I can make speeches about uniformities, but now is not the time. The non-expansiveness rule, which is for many years people complained about it when we presented this work, is that basically these operations have to be non-expansive. So that's like the analog of the congruence rule in ordinary equational logic. And then we have substitution in the usual way, a cut rule when you're cutting things, and an assumption rule that says if phi, a particular quantitative inference, is in your set of assumptions, then you can certainly deduce it. So those last three are standard, but the ones above are basically capturing the usual kind of metric reasoning. So it's basically a logic of reasoning about metric structures, if you like. Not surprisingly, we're going to get monads on Met. So the quantitative equational theory is the smallest deducibility relation containing some set of assumptions. So you write down some equations, and then you say, close it under all those rules that I had on the previous slide, collect that, and now that's a quantitative equational theory. Okay. Now let's do algebras. So we've done the quantitative analog of equational logic. What's an quantitative equational algebra, or what's a quantitative algebra equationally defined? So again, it's an ordinary omega algebra, except the carrier is now required to be a metric space. So you have a signature just as before. All the functions in omega are required to be non-expansive. Morphisms are omega algebra homomorphisms that are also themselves non-expansive. So before they were just homomorphisms, but now they're non-expansive homomorphisms. And since I have metric structure in every one of my algebras, I can require them to be non-expansive. Now, this term algebra that I built before is an example of an omega algebra, and not yet quantitative. It's just an omega algebra. And so substitutions can be, which are just assigning elements of A to variables, can be extended to omega homomorphisms between the term algebra and A. What does it mean? What does it mean to say one of these algebras satisfies an equation of this kind, where I have a bunch of assumptions, let's say n of them, and a conclusion? So what it says is what you might expect. For any substitution such that the images of the terms under that substitution sigma respect the distance relations, now using the metric of the algebra into which you're mapping it, if it respects all those constraints, so sigma of S sub I and sigma of T sub I are at distance D, distance less than or equal to epsilon I as measured by the metric D, then that particular equation constraint is satisfied. If all of them are satisfied, then it must be true that the same constraint is satisfied by the terms on the right-hand side of the turnstile. Just as you would expect, it's just a quantitative analog of what it means for ordinary algebra to satisfy an ordinary equation, except things are now at metric distances rather than being equal. And we use this notation with a subscript A. Can you see my hand when I use it on the screen? Yeah, good. So when I put this subscript A, I mean that algebra A satisfies this equation. So I'm going to write K U omega for the set of algebras satisfying all the equations of some equational theory U. We can put a metric on this term algebra, which hitherto had just been a term algebra. So what we're going to do is we're going to say, using the equations of my theory, I'm going to try and prove equations between S and T. And then I'll take the inf over all the equations that are, over all epsilon, such that I can establish S equals of epsilon T from my theory U. And that indeed defines actually not quite a metric, but a pseudometric. And this pseudometric can take on infinite values. For example, if I cannot prove anything. So it makes sense actually to use infinite values rather than restricting it to 0, 1. Now, this is a pseudometric, but pseudometrics define an equivalence relation in a natural way. So 2 points are deemed equivalent if they're at 0 distance. That equivalence relation is called the kernel. And when you quotient by that kernel on the resulting quotient space, the pseudometric restricts to or projects to an ordinary metric. So we can take this kernel, it will be a congruence for our signature, and we take the quotient, we get an extended metric space, proper metric space, not a pseudometric. So the resulting algebra is indeed in K omega U, because we used the equations in U to prove, to give you that metric. Now you can do this for any set of generators and produce a free algebra, not just the terms that you construct from variables. So you get free quantitative algebras now, satisfying quantitative equations. So the first important theorem we showed was the analog of Birkhoff's completeness theorem. If you look at all the algebras in your equationally specified class of algebras, and it turns out that some equation is satisfied by all of them, then this will happen if and only if that inference is actually in your theory. Okay, so this is so it's the analog of the usual completeness theorem for equational logic. From right to left is essentially by definition, but the left to right, one has to do an explicit model construction. So the plan is the same as the standard proof, plan of the standard proof, but you have to do a lot of fiddling to get the quantitative aspects right. And it uses the infinitary rule in a crucial way. Now, I talked about from a set, you can construct a free algebra. But in fact, you can start from a metric space and construct a free algebra. So what you do is you're starting out with a metric space M given a distance D. So what you do is you add a constant for each element of the metric space. And then you add axioms that encode the distance information from that metric space. So for every rational number E, such that the distance from M to M is less than E, you add this equation M equals sub E n. Why rational numbers? Because I required things to be rational before, which is going to be useful for, which was useful when we proved completeness. But of course, the rationals are dense, so you can always encode the information of real valued distances by using lots of rational equations like that. So now I've taken my operators, my original constants, and I've added all these new constants and all these new equations to encode all the information about M. So I'll call this extended signature omega sub M, the extended theory that I get U sub M. And now I can build the class of algebras K of U sub M. And sorry, that should be omega sub M U sub M. By forgetting this information about M, I can view this as an algebra and K omega U. And so what I've done is I've built essentially a free algebra from a metric space. So given any non-expansive map from M to A, where M is the metric space I was started with, and A is any quantitative algebra, which of course has to be a metric space too, we can turn this algebra into an algebra in the extended sense of omega sub M U sub M by interpreting each constant M in that structure as an element in A as dictated by alpha. So every map from M to A extends to a homomorphism from the term algebra that you've constructed based on M. And again, it has the obvious universal property, and you can indeed go on and show that this produces a monad on the category of the extended metric spaces. So just as you had monads coming from algebras defined equationally, you have monads on MET coming from quantitative algebras defined by quantitative equations. Okay, so all that was, maybe it looked like theory for its own sake, but now I want to do the example that I found so, that made me at least want to do this. Let's go back to Stone's algebra. So these are the axioms we had before. There were uncountably many operations, but now I'm going to add a quantitative equation. And this equation says, if I take X and Y, and I combine X with Z and also combine Y with Z using the same convex combination plus sub E, where E is something less than epsilon, then this equation will hold. This is, of course, not axiomatic or anything. I'm just saying now I'm requiring this as a new equation. Looks a bit silly. Why did you come up with this one? Well, you can ask questions now. Here's a bunch of equations. Here's some operations. What do the free algebras of this thing look like when I build them on the category of metric spaces? So the last equation uses one of the new epsilon indexed equations in a non-trivial way. And we call it the left invariant axiom scheme. I don't know, it's just because the thing on the left doesn't change. But the important thing is, what does this axiomatize? What do we get when we look at the free algebras of this? Magic. You start with a metric space. The free algebra is exactly the space of Borel probability measures with finite support, and the metric on it is the total variation metric. Nothing was mentioned about probability distributions. Nothing was mentioned about that particular metric on probability distributions, yet it popped up from these equations. So I'm reminding you what the total variation metric is. It's the soup over all measurable sets of the difference between mu of E and U of E. And so, as I said, there's a duality theorem. Now, couplings, as I defined before, is a measure on the product space whose marginals match. And now, if you take the set of couplings and you write delta for the diagonal of M cross M, the total variation duality theorem says the total variation metric is the minimum over all couplings of the size of the complement of the diagonal. And I say min rather than inf, it's because the min is actually attained. So this was this together with some basic facts like convex combinations of couplings are couplings, and some other technical lemmas about how you can split probability measures into pieces that allow you to do some combinatorial arguments. We were able to prove that the freely generated lib algebra from a metric space is precisely the finitely supported probability measures on M, where you interpret this abstract plus sub E operation as convex combination. So you endow this with the total variation metric to make it a quantitative algebra, and then you can show that this quantitative algebra that you get is indeed in the class of algebras. It satisfies all the equations that we want. And in order to prove that, we use the lemmas that I just alluded to, convexity and the splitting lemma and things like that. And then the theorem you can then prove is that it is in fact isomorphic to the free algebra generated by M. And this last proof requires the embedding of convex spaces into vector spaces. So it's kind of a representation theorem that's Stone proved for these abstract convex spaces. So somehow these equations out of the blue give rise to the total variation metric. But there's a much more compelling example to me. So we go back, we ditch that axiom I added, go back to Stone's axioms, but now add this one. So this one has a couple of assumptions, unlike the Li axiom. It says I'm making some assumption about the distance from x to y and the distance from x prime to y prime. And now I'm taking the same convex combination of x and x prime and y prime. And that will satisfy an equation with a certain delta, where delta is given by this formula, an upper bound on convex combination like that. These p's and p truths and all confuse things a bit. So let's look at the special case where p is equal to 1. So it looks like this. If this is at distance epsilon 1, that's at distance epsilon 2. I take this convex combination, then the distance between them is bounded by the same convex combination of epsilon 1 and epsilon 2. A requirement. Some algebras may satisfy this, some may not. So now we can ask, what kind of algebras satisfy this thing? In particular, what kind of algebras, what does the free algebra look like? So let's take a look at a picture of what this axiom is telling us. So there it is, x and x prime, y and y prime. So there's some distance between x and x prime, x and y, and between x prime and y prime. And that distance, those distances we'll call epsilon 1 and epsilon 2. Then you take the convex combination of x and x prime and the same convex combination of y and y prime. The distance between them will be the same convex combination of epsilon 1 and epsilon 2. So this trapezium is supposed to give you a pictorial idea of that equation. So the question remains, what are the free algebras of this? So recall Kantorovich, we have the W metrics, the Kantorovich metric, and the duality theorem. So we used duality before, a simple kind of duality to prove the total variation property. This time we use the Kantorovich duality theorem, Kantorovich-Rubinstein duality theorem to prove what's coming up. Again, we take the finitely supported measures on M and interpret it as a barycentric algebra as before by taking the plus sub E to mean convex sums. We give it the WP metric and then show that we actually get an algebra satisfying this interpolative axiom that I enumerated. This uses the definitions of the WP metrics as an inf and convexity of couplings and various other. It's quite a long and technical proof. We prove splitting lemmas and show that again that we get that this construction that I just described gives you the free algebra, but it has slightly more involved arguments, but the spirit of the proofs are essentially the same. You might be dissatisfied with all this thing about the, oops, excuse me. Sorry. So you might be dissatisfied with all the stuff about finitely supported metrics. You would, finitely supported probability distributions. We would like to look at ordinary measures in general. So we'd like to ask, how do we lift all this to the continuous world? So let me talk about convergence of measures for a minute. In what sense can we talk sensibly about convergence of a sequence of measures? What does it mean to say I have a family of probability measures converging to something? So it's done via integration, of course. So if you have a suitable class of functions, then one sensible notion of convergence is to say, I will say that the family mu sub I converges to mu if for every f in my class of good functions, this sequence of real numbers obtained by integrating f converges to this number, also obtained by integrating f. Okay, so this has to work for every function in my class. So the class to consider, in fact, is bounded continuous functions. So if you take the class of bounded continuous functions and define convergence in this way, you get what's called weak convergence. Okay, so these WP metrics also, this notion of convergence is called weak convergence. It defines a topology on the space of measures called the weak topology. And the WP metrics that I defined before actually metrize that particular topology, the topology of weak convergence. The important point about all this is that those finitely supported probability measures I was talking about are dense in the space of all probability measures when endowed with this weak topology. And this weak topology is the one, in fact, that probabilists use. So it's not some crazy thing I've cooked up just for this purpose. So now, instead of working with arbitrary metric spaces, we're going to work with complete separable metric spaces. Sometimes, so the underlying topological spaces of complete separable metric spaces are called Polish spaces. And every measure theorist knows that these are the spaces that everyone loves. So you define capital delta of M to be the space of all Borel probability measures on a complete separable metric space. We give it the WP metric and interpret plus as convex combination. This gives you an IB algebra. Now, if you construct the term algebra as before, but this time you complete it in that metric, then you'll get an algebra exactly isomorphic to this one. So this time, the free algebra suitably completed gives you all the Borel measures with the Kantorovich metric. So what was striking to me about all this is we didn't say anything about Kantorovich metric, couplings, transport problems, optimization, or any of those things by which the Kantorovich metric is defined. We added this one rather naive looking quantitative equation, which looks like some kind of simple linear interpolation requirement, and boom, out of black magic, free algebras that we constructed give you exactly the Kantorovich metric. So since then, we've done many, or not many, we've done some other examples. So the Hausdorff metric also can be shown to arise as the free algebra of a suitable structure. So that's kind of what I wanted to say in terms of technical content. I'll just conclude with some remarks about what we've done and since then. So these quantitative equations give a handle on otherwise arcane things like those WP metrics. As I said before, one simple equation seems to produce them. I would like to leverage that and see if I can get some nice algorithms to compute the WP metrics. So we've also done this for Hausdorff metrics. We've considered pointed barycentric algebras, and we've considered Markov processes, which are basically probability distributions evolving in time, for which we've also given equational axiomatizations. So we've proved variety theorems, and also other people like Stefan Milius and Henning Urbat have proved variety theorems. Other people like Iji Adamek have considered the theory of monads on these extended metric spaces given by these equations, and so on. So this last work of Iji Adamek's I mentioned is in LIX this year, which was presented just a couple of months ago in Haifa, where I was last month. So in other extended work that we've done, together with a fourth collaborator, Giorgio Bacci, we have defined what it means to take the sum of a theory and to take the tensor product of theories. So work like this in the ordinary equational setting had been done by Plotkin, Power, maybe Paul Levy, but Plotkin, Hyland, Plotkin, Power, Paul Levy, and people like that. So they defined sum and tensor of equational theories. So we've done the analogous thing for quantitative equational theories. What does it mean to take the sum of two theories, the tensor of two theories? And we've shown various structures like Markov processes come out as sum. And for example, labeled Markov processes or MBPs come out by taking tensor of these quantitative theories. We've also added fixed point theories into the framework. So that was another LIX paper from last year, where we showed how to add essentially reasoning in the style of the Banach fixed point theorem to our equational reasoning principles. And defined things like the analog of those things that iteration theories and so on, which were done again in the purely non-quantitative setting. We've done quantitative analogs of that. Very recently, again in LIX this year, Ralph Sarkis, Matteo Mio, and Valeria Vinudelli have introduced an idea called lifting, and this allows us to do much more general things. In particular, they can drop non-expansiveness, but you can also now work with distance functions that violate all the conceivable axioms you might have for metrics. There are even versions that violate the reflexivity axiom, which turns out to be an important example that we came up with in work I was doing in machine learning. I should have possibly been the one to then also do this extension, but they did it before we did. And so now it's gone quite a bit beyond the framework that I described in this talk. And as you can see, people are working actively on it as we speak, so to speak. All right, I think I've hit 8:01. So I'll stop here.
Okay, thank you very much. Mike Barr just logged off like 2 minutes ago.
Yes.
But any questions? Anyways, it's a whole world. Wow.
Yes, the whole world. And as you can see, there's like 4 or 5 papers that we've written after the basic one, which came out in 2016, which was
very nice.
Yeah, I'm quite pleased with it. Thank you. I'm very pleased with it. There are a bunch of things one can do, though. One of them, I'd like to get some kind of complexity theoretic results on, which I don't have any yet, but we're trying to give bounds on the size of proofs and so on. And when I have results, I'll tell you. One thing that I've not made any progress on, possibly because I haven't tried hard enough, but also possibly because I just don't have the right skill set. I'd really like to say, okay, this Kantorovich metric, which everybody's dying to compute, and which is an expensive optimization problem to compute, is, there's infs and soups and all, you can write them very casually on a slide. But if you want an algorithm to work them out, it's computationally complex. So I felt that since we have this simple equational description, there must be some way of at least approximating Kantorovich efficiently, and I haven't seen it yet.
No, I don't know. Anyways, but when you when you do figure it out, you have to come back and tell us. Anyways, okay. Prakash, thank you very much. Thank you.
Yes, thanks for a really nice talk.
Very nice, very understandable.
Yes, I guess it's this was not a topic that people in category theory generally want to hear about. So
this is pure. This is very nice. Anyways, so let me just say, next week James Torrey will be talking about diagonalization and the limits of limitative theorems.
So yeah, I was curious about that. By the way, are you still recording?
Yes, but I can stop. Okay, I'm stopping. Anyways, Prakash, again, thank you very much.